So today, in this last lecture, I will try to convey the axioms for synthetic category theory. I won't give you all of them because the list of axioms is long. It's around 20 or so. And the problem is that in order to state them, you have to prove intermediate results along the way. So I will admit a few steps also, in addition to omitting some axioms. But I will try to give you the most important of them. And so the idea is that we want a theory that looks like ordinary category theory, including when we manipulate statements and proofs. And also what is very important is that we want to internalize everything. That is, at the end of the day, what we want, in some sense, this is where the theory actually starts. When you can start to do mathematics, is that you want to define the synthetic category of categories. And so in some sense, what our goal will be also to define what that is. So what we start from is, so we define dependent type theory. And more precisely, a generalized algebraic theory. And then, because this is our goal, so we call types synthetic categories. Yeah? And then we want to add enough axioms so that at the end of the day, possibly with forgetting that, because in some sense we don't want to speak about anything else, so we could define this to be categories. But in secret, it's more infinity categories. But the idea is that there is nothing else, so there is only one kind of category anyway. So I will use synthetic to insist on the fact that it's not ordinary category theory. Also, it could. Maybe if I have time, I can explain what kind of axiom we can add so that this is literally the theory of infinity categories, the way they are constructed within classical mathematics. So you can force the theory to be extremely classical. But apart from that, so I will say either synthetic category or category. There will be a little bit of ambiguity because I won't give you the formal syntactic rules because they are very long. You have inference rules and so forth. So I will pretend, and I hope you will cope with me, that types, they form some kind of category, the syntactic category, and that will hide a lot of technical details. So they form a kind of, and you could say, an ordinary, category. And the first axiom we will ask is that with finite products, so in particular, you will have a binary product and an internal ohm. That I will call fun, like functor. And that is because, so whenever we have two categories, we want to say that we have the category of functors. So far, this is where we are. And now, remember that whenever we have a type theory, so types are also contexts. Yeah? So if you take gamma, a context, or here it would mean a synthetic category, then there is the syntactic category of types over gamma, so types declared in context gamma, and it is also a semantic interpretation of the type theory we are going to define. So far, because I didn't ask for a lot of axioms, actually, no, already it failed, so this is also a dependent type theory. But in there, but already it won't satisfy all the axioms I'm about to say. In particular, it starts already here. It won't have an internal ohm. Unless gamma is a groupoid. I will define what groupoids are. later on. But the idea is that we need to define enough structure in our language to actually make sense of that. And only for groupoids, this would be a semantic interpretation of the theory we are dealing with, and otherwise it won't. Okay. So, but this is a type theory nevertheless. And so a lot of the features of type theory remain true here. And so I will take advantage of this, at least implicitly. Now, if you do category theory, so maybe I should introduce groupoids first. So I won't give you all the axioms, but if you think about groupoids, so in ordinary category theory, these are just categories in which all morphisms are invertible. And if you have an arbitrary category, there is a subcategory with the same objects, but when in which you only take the isomorphisms and give you a maximal subgroupoid of a category. And so that is a way to produce groupoids from categories in a very nice way. And so this is exactly how we introduce it. So we introduce in our axioms an operator which associates to each C twiddle. Yeah, so far it's just another type. And then we want that it is a subcategory of C, at least, because it should be the subgroupoid. So remember that in type theory, you just have to say that to any term, C correspond a term I of C in C. In other words, when I say it as an axiom, so I stipulate that there is a map, and it is in the freest possible way. And then I will add more axioms to express to make it look like the comonad associated to an adjunction or something like that, and that will be fully faithful and so forth. But I propose not to go in detail with that because that is not so interesting. But we put enough axioms so that it behaves exactly the way you would imagine if you imagine ordinary category theory. This is what the axioms are designed to do, and so we just do that. Okay, and then once we have groupoids, so the idea, the reason why it will look like infinity category theory as opposed to ordinary category theory is that in infinity category theory there are no sets anymore. And so whenever you have sets in ordinary category theory, you should have an infinity groupoid. And here, because everything should be infinity categorical by default, so what I call groupoids, they should in fact be infinity groupoids if you want, like more like it would behave more like a homotopy type in some sense. And that means that whenever you speak of a collection of data, it won't define a set, it will define an infinity groupoid, or simply a groupoid, the way I will define them in a couple of minutes. And so in particular, if I want to speak of the collection of functors from A to B, for instance, I will call that, for instance, map. And what is a collection? Well, you take the category of all functors, and then you can apply twiddle to it, and that is a collection of functors now. And that is the best thing you could have as collection so far. Okay, then as I said, you have finite products. That means you have a terminal object, and because I'm used to simplicial notations, we use simplicial notations at least in no dimension. We'll go up to 2 only. So in this theory, we don't need to know how to count above 2. And we'll define, as a consequence of the axioms, we have a natural number object, and then we'll be allowed to count further. Okay, so let's pretend we start at 0. This is the terminal object. Or if you want, the empty context, if you remember. And then we stipulate as an axiom that there is something, a fixed object, a constant, that is called delta 1, and that will play the role of the interval. And it has 2 morphisms. Called 0 and 1. There are other axioms, maybe I will say it orally, so we will ask that some finite coproducts also exist, and there should be universal in the same way they are universal in topoi, for instance. And we'll ask that the induced map from the coproduct of two copies of the point delta 0 to delta 1 is an embedding in some sense, but I propose to not to state that explicitly. So now the idea is that now a morphism in a synthetic category C is a functor like this. Yeah, that's what this guy is there for. He's there to define what it means to look at morphisms. So far, so good. Now, we will, when we have such a morphism F, then we can compose F with this map 0. I will call that X. I can compose F with the map 1. I call that Y. And whenever I have these equations, then I will write this or that, depending on the mood. Yeah. And then I try to introduce the language of diagrams in a category just because I introduce this objects delta 1. See, it's very poor, low-level thing, and we don't need anything else. Now we would like to speak of compositions. We want to say that we can compose morphisms. So for this, we have to introduce more axioms. Again, I won't go into the details because this is actually a very interesting story. You have tons of little things you can try to do, and it is very interesting to make them agree with each other. But I won't have time to go into the details of that, so I will give you one aspect of it. And a very quick way to say it is that we add as an axiom that delta 1 is a bounded lattice with initial term 0 and a terminal term. So I should say terminal because otherwise 1. And this you can explain very easily because what it means essentially is that remember you have finite products, so you can form delta 1 times delta 1. And there is an operator that is called maximum, another operator that is called minimum. And you have to say that they behave like the way they deserve their name. Okay? And so forth. So I propose not to say that. But you see, they are very important because you see, if you want to do homotopy theory, you see, when you use these simple things, this is how you speak of contractibility. So one will express the fact that 0 is an initial object of delta 1, and the other one will express that 1 is a terminal object of delta 1, and stuff like that. It's already built in this sentence, in some sense, which we expect from delta 1. Yeah? It's supposed to be the universal guy that represents morphism. So it should have a structure of this form. At least it's natural to think it should. Okay. Now, using this, you can produce projectors on this delta 1 times delta 1 that correspond, because if you think of delta 1 times delta 1 like this, so basically it's a shape of this form, and then you have a diagonal. And that means that you have two triangles in there. And so the idea is that you can define two projectors. One of them will have the image of the upper triangle, and the other one have the lower triangle. And it's an exercise to do it using these two operators. And so we'll ask that the two projectors. So if you call this, I don't know, 1 and 2, defining 1 and 2 are representable or have an image. And the image is called delta 2. Yeah, it's one of these. And then you can show they are isomorphic, but let's say you choose one of them. I don't really care so far. Then the idea is that now you have delta 2. It's one way to have access to it. There are other ways, but I will only speak of that for those who are interested another time. And so the idea is that now, maybe well, I should erase it. So now that we have delta 2, it means we can speak of, so delta 2, you should think of it as something of this form, in some sense. And then what is a morphism or a functor to a category C? Then this is exactly what you should define as a commutative triangle, so little t. And whenever you have such a thing, so you can prove using these operators that you have 3 morphisms from delta 1 to delta 2. Yeah. So it is a morphism that embedding delta 1 and avoiding I. And so you can do that for I equal 0, 1, 2. And of course, depending on your definition, so this could be 0, 1, 2, for instance, and you just rename these pairs, whatever, this is what this would be. And then check that you can do that. In particular, so if you take delta 2, it means you take this edge here. If you take delta 0, it means you take this edge. And that means that you can speak of whenever you have t, you can take t composed with delta 2, 2, that would correspond to an edge of this form. Then t delta 2, 0, that corresponds to an edge of this form. It's g. Yeah? And then there is t of delta 1, 2, that is an edge of this form, call it h. And then the way I like to write it is that now it means that in our category, synthetic category C, we have 3 morphisms, and in the middle we have a triangle that witnesses the fact that f and g has a composition, namely h. Okay? So if you have 2 pairs, if you have a pair fg, we say that f and g have a composition if there is such a triangle T. Yeah? And then, or you say that an edge h from x to z is a composition of f and g if there exists T so that this is true. So now I would like to say that there is a unique composition. Yes?
So delta is just a face map here.
Yes, exactly. So what we want now, we want to say that there is a unique thing, so we should be slightly, remember that last time I introduced an idea that is due to Martin Löw. He's a philosopher, not a mathematician or a computer scientist, who introduced the notion of identity type. And so in our theory, we ask for identity types. That means that now for any term in some category C, there is a type of identifications of these terms. And so it is, by default, it is simply, for the moment, it's just a category. The consequence of the axiom is that it will be, in fact, a groupoid. That I will come back to the definition of groupoid in a couple of minutes. So for the moment, it's just a category. And so a term of this it will be a proof that x and y agree. But at least, and so when I said, for instance, that the equality x equal to y holds, well, in natural language, what I'm saying, in fact, is that I provide a term of that. Yeah, but if you want, the name of this term will be the sentence I say in natural language, and then it looks like formal things. And so once you have this, then for 2 categories, we can form the category of equivalences. Yeah, because whenever you have the identity type, we can say what that means. And then again, to provide the term in there, it means I will say that C and D are equivalent. The same way you can define, for given a functor, you can define the category. That means that this functor is an equivalence, for instance, and providing a term would be the assertion that this functor is an equivalence, and so forth. So I will speak in natural language, but the idea is that the fact that everything is well formed, you should check by actually checking and proving rigorously that every sentence you say can be translated into an actual category. And whenever you claim something, it's because you provide an object there, a global section of it. Okay, so I go on with this. So now we can speak also of homotopy pullback squares, because we can, or pullbacks in general, because whenever we introduce the identity type, we can do the following. Whenever you have a functor, say f and g going to the same with the same target, now you will define the product, the fiber product. And so for this, you have to define, so type is essentially determined by its terms. So you have to say what are the terms of this fiber product. And so the terms of this fiber product are, there should be pairs. So you should have a guy, little a in capital A, little b in capital B. And then you should say that they are equal. But again, because we are doing things constructively, so we cannot say that they are equal in a silly way. So you have to provide a proof that they are. So they come. So a term here is a pair together with a proof, call it sigma, such that, so when you have this, so you can look at f of A and g of B. Now these two things are terms of C. That means that you can provide the type of equalities, and then to say that they are equal, it means you must provide a proof of it. And so a term here is exactly such a thing. It's a pair together with a proof that they are equal. Yeah? And if you think of what you do in topology, it would correspond to the homotopy fiber product, because you could think of this as the space of passes from x to y. And that means here you are taking the homotopy fiber product. When you look at, it means this sigma would be a pass from f of A to g of B. Yeah? And now you can speak of, so you can see that whenever you have a commutative square of functors, you will have a canonical functor to this fiber product. And then you will say that a square is an homotopy pullback square if the induced map to this very explicit fiber product is an equivalence. And again, we know what that means because we define identity types. So homotopy pullback squares are defined. Okay? Good. And that is very interesting because now if we look at everything we have, so we have the Seagal axiom, or Seagal, we should say also maybe Grothendieck axiom, but I don't know. Is simply the fact that if you look at fun delta 1, fun delta 2 to C, sorry. Then you can look at fun delta 1 to C, fun delta 1 to C. Here, so you should think of these things are restriction, and they want to do exactly this operation of from a triangle T, you take F and G. This is what these two things are supposed to do. So if you want to say that this is F, I guess it's because here you call it delta 2, say upper star, and you precompose with it, and you get F. Or you could precompose with delta 2, 0 upper star, you get G. And now you want to say that they agree, that is the codomain of F agrees with the domain of G. So you have to take so delta 2 was the codomain of F, that is you evaluate at 1, and here you evaluate at 0, and this is a pullback square. And we know what that means because this commutes, that is for silly reasons, therefore we have a canonical functor from fun delta 2 to C to the fiber product defined on the left, and you ask that this comparison map is an equivalence. Yeah? This is how you state it. And that means that That means that now, given any pair of morphisms in C, having the appropriate source and target, there is a unique composite H. Unique up to homotopy. That is the category, the object that classifies all possible compositions will be equivalent to a point. So in particular, it is non-empty, and any 2 points are canonically equivalent, and so forth. So it's unique in some homotopy theoretic way. And that means you can compose morphisms in categories. So far, so good. Once you can compose them, you can remark that you have also identities. Yes. Because you simply remember that there is a canonical delta 0 is the terminal object. So if you call it P, you can do P up a star. And then the image of X, you call the identity of X. Yeah? So any object has an identity. And now, because you know what it means to compose, you can say that a morphism has a left inverse and a right inverse, because you can compose and say that there exists a right inverse and so forth. And now you can say what it means for a morphism to be invertible. Okay? And now, as an axiom, the following properties are equivalent. Is that C, the map from C twiddle to C is an equivalence. And 2, all morphisms of C are invertible. So I don't prove it, I just claim it as an axiom, but now see, it says that this abstractly given operator, C twiddle, indeed provides you a universal category going to C in which all morphisms are invertible. Yeah? So it means it really starts to behave the way we would expect from the maximal groupoid. And now we can define groupoids. C is a groupoid if one of these equivalent conditions is true. So for instance, if I from C to C is an equivalence. And now the idea is that so the principle that should follow is that even if I don't say it explicitly, either by definition or you have to prove it, because that's important that it is true anyway, for a reason or another, is that for any groupoid, say gamma, the syntactic category of types in context gamma is, and more precisely, I mean, is a semantic interpretation of our logic. That means everything I said should be true in there, and everything I will say will also be true. Yeah? Absolutely everything. That's a guiding principle to introduce axioms properly. As a remark, when you do that, you are forcing yourself to prevent yourself to use sets. Because even if you use ordinary category theory, you are really, you see, you can speak of the one groupoid of objects and so forth if you want in ordinary category theory. But if ever you start to speak of sets, and it won't hold there. Yeah? So you really are forced to forget about sets by doing that. But it's really, in some sense, it also simplifies a lot of things. I mean, it's also almost allows you to consider groupoids as discrete objects, in fact. It's really a simplification and really gives you much more freedom. So, but it is one of the places where you should forget about sets, at least for a while. Of course, you can come back to them eventually. But you should do that only if you are interested by them in some, and of course you can have good reasons to do this, but for the moment we don't need them. Okay, so I define groupoids. So what I should say is that also a consequence of this Seagal axiom is that maybe I should, yeah. No. So you could look at the evaluation at 0 and 1, and whenever you have a pair of objects, then you can form the pullback. And then it gives you the category of morphisms from X to Y. But in fact, because delta 0 is a groupoid, you can check that every map in there is an isomorphism. That is an exercise, easy. So that means that you can put twiddle instead, and actually you can prove, as a consequence of the axioms, maybe, okay, not yet, but with other axioms it will be true. So you can take it for granted for the moment, that this will be a pullback. That is a way to say a particular case of the fact that a natural transformation is invertible if and only if it is object-wise invertible, and that will be a consequence of the axioms anyway. And so what I mean is that when you take this pullback, either you can consider it as a pullback using the language of categories, but you could also restrict to groupoids, and it will be also a pullback. And that is a proof that, in fact, this is a groupoid. So it is the closest you would get to having a collection. So in this sense, that's why it's more a model of infinity 1 category theory as opposed to infinity n with n bigger than 1, because between two objects, you only have a mere collection of morphisms, even though if collection means higher groupoid. Yeah? But a consequence of this egal axiom is that if you have three objects, you have now a composition law, which is really unique, at least up to homotopy. Yeah? Or up to, I mean, here I say homotopy because I'm used to models or whatever, but we have only equality here, so it's really unique, period. In the precise sense of the logic we are defining. Okay. So now we introduce the univalence. So it's the analog of Voevodsky's univalence, except that we state it for any object, any category C. So if you take C, any synthetic category, you take X, Y. Maybe I'm too. So it should come before that. So an object. It is important to have objects of a synthetic category is a term of, say, if it's called C, of C twiddle. Yeah. And so the idea is that it will be an object-oriented theory eventually. For the moment, it doesn't look it is. So I will explain an axiom that makes everything works. But we'll focus on objects as opposed. So it's a very particular kind of term. Yeah, it's more restrictive. And so remember that a term is supposed to be an arbitrary functor. And in fact, I could even restrict and be more precise in the fragment of the logic corresponding to groupoids. That means you should really consider an object X as a functor from gamma to C when gamma is a groupoid. You see, a general term, it's a general functor when gamma is arbitrary. And an object is just an arbitrary functor, but gamma is a groupoid as opposed to an arbitrary category. This is really what objects are. And then if you think about it, there is always a universal object, which is the inclusion of C twiddle in C. Yeah? And when you write equation, you have to see when you do basic analysis, when you learn calculus and stuff like that, you write your functions f of x. Yeah? When x is suppose your element in your real line or whatever. But what it is, in fact, this x, it is the identity of the domain of your function. So you could also say that x, you could call x, it would be the generic name of this inclusion. And so when you write f of x, when x means that, it would really mean that you work object-wise. and it is correct. Yeah? This is how it works. Anyway, so whenever you have a pair of objects defined in the same context, gamma, it should be a groupoid. Now, what we can do is consider the groupoid of identifications between x and y, or because now we know what it means to be invertible, you can write it with equations, and that means with appropriate pullbacks, you can define the term of isomorphism from x to y. So it's really, it will be a kind of a subcategory of all morphism from x to y that consists of guys that have the left inverse and the right inverse. And you can write this as a term, as a wave-form type, and therefore as a category. And the idea is that the identity of anything will define an isomorphism, and from this you can deduce there is a canonical comparison map. And you ask that this is an equivalence. Yeah. Because you see, otherwise we would have several ways to identify objects. And the point of view of univalence is that we are forcing that there is only one way to identify. So if you want to preserve this principle, it means that whenever you create a new way to identify, then it should be identified with the one we have, because the one we have is in fact the freest way possible. You see, it's a way to define equality, but with no constraint at all, so it's completely free. And here we are saying that it's less free in some sense. It's related with the idea that we can compose morphisms and so forth, but we will force all these things to agree, because we want a theory when there is absolutely one way, only one way to identify terms and objects in general, and so there is this is what we are claiming. Sorry, maybe I should have. Okay. And so delta 0 is a groupoid. So, yeah, so what I was saying about the previous question is that so the goal is to define the synthetic category of categories. And that means that now if you have a category, I should sing or something. But I don't think very well, so I won't do that. So if you have a category, at the end of the day, when we have finished our program, we can consider a category as a type, the way it was defined to begin with, or as a term of the category of categories. And we want the directed univalence will imply that that it is really equivalent to consider them as terms of the universe or as a category externally. And therefore, we can apply this univalence principle because we will apply it to categories as terms, for instance. So it will be that is one way to see that the univalence, in the classical sense, will apply to categories themselves. Yeah. But we are not there yet. We are on our way to it. I think I'm going very fast, so you can stop me whenever you want. Otherwise, I mean, I'm happy to proceed. I have a lot of things to say, so. But really, do not hesitate to stop me. I don't mind if I don't say everything. Go. So now, maybe I should come back to how we define the universe of sets, because I said it yesterday, but maybe I didn't convey it in a nice way. Because remember, so it is a parenthesis, aparté. So in set theory, so you can think of the collection of all sets, and remember, this was defined, set dot is the set of sets equipped with a base point, and we forget the base point. And then the idea is that we call the sets that belong to this collection small. And so what does this do? It is a universal. So as I said, you can, if you have a set saying that it is small, means that you have a pullback square of this form. But now, if you replace the point by an arbitrary set, and you have a map F, what does it mean that a map F fits into such a square? It means literally, and nothing else than the fact that each fiber of F is small. So in some sense, you could think of this map as the universal map between sets with small fibers. And you see when you want to define a universe of types, which is what it wants to do here, so what you want to do is not to classify objects. You want to classify a class of maps. Yeah? And so the way we will define the universe of categories is that we will define a class of maps, of functors, and we will define it as classifying this class of functors. And so the axiom will simply say that it exists as such a classifier, and therefore it will be defined by universal properties, so it will be uniquely determined, and this is how we will proceed. And so so here, so it means you have to understand what are functors in the category of categories, and it is well known, these are the co-Cartesian fibrations. So we have to define co-Cartesian fibrations. And the way we do it, and that's the beauty of it, is that once we have this kind of language, we simply say exactly the same definition as usual. We don't change a word, a comma, anything. Yeah? So I will do it, but really there is absolutely nothing new, and this is the point of it. So consider a functor, say from x to b. So we say a morphism, so v from b0 to b1 in B, and we consider a lift of V, and what we call a lift of V is a morphism U from 0 to x1 such that the image of U is V. And so here you could say, when I say this holds, you see, I mean that there is a witness of this equality. Yeah? But I won't say it, or I call it such that. Okay. Then this is what lifts are. And we say that U is P locally, or locally P, locally P co-Cartesian. I mean, in SGA1 they are simply called without the adverb locally, but in modern times, if you want to define co-Cartesian fibration as opposed to locally co-Cartesian fibrations, it's better to distinguish a little bit. If for any lift of the form, so any lift of U again, or V, sorry, so U prime from x0 to x1 prime, but with domain x0. So again, such that there is a unique morphism, I don't know, say W from where x1 to x1 prime, such that that is a lift of the identity. And of course, when I say, you see, I say it in natural language, but what it really means is that there is, in fact, whenever you look at such another lift, you can define a category of such gadgets W together with witnesses of these equalities. And I ask that this category is equivalent to a point. This is what this sentence means. Yes?
Does the data of the lift include the data of the proof?
Yes, always. It's a general thing. Like we always keep track of proofs. Always, 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 always. This is what these sentences mean. Otherwise, I won't write anything. But yeah, and otherwise, I mean, there are types that are called propositions. Maybe I'll come back to that if I don't think I will have time, but if ever I have time, I can come back to that. Types that are, in fact, sub-objects of the terminal object. And so if ever a statement is a proposition in this precise sense, then you don't have to keep track of proofs anymore, because if they exist, these proofs, they will be unique. But the propositions are very peculiar. But of course, I mean, a statement from classical mathematics usually are propositions. That's why we don't keep track of proofs in classical mathematics. That's all. a priori, we don't expect to have classical mathematics arising from nowhere, let's say. It should be more general. Yeah, so now what it means to be a co-Cartesian fibration. So definition. So P is a co-Cartesian fibration if it has three properties. So the first one, that is a technical one, is that it should be defined as a relative type, that it comes from a type defined in context B. Remember, this is how I write them. But in words, it means that it comes from that. That is a very technical thing. It's not really important. If you avoid the first part, it just means that as opposed to what you would define as a co-Cartesian fibration in the classical sense, you would define functors that are co-Cartesian that can be written as a composition of an arbitrary equivalence of categories and then a co-Cartesian fibration in the classical sense. Since we work up to equivalence, we don't really care. But if you want to have a definition that really looks like classical thing, you should put that in addition. It's not a big deal because up to equivalence, any functor is of this form, in fact. So that's why, I mean, it's not really, you can forget about that if you don't want to think about it. In some sense, it would make sense to make it go away, but I don't know. I'm used to it myself, so I introduce it. And then the important thing is that now any morphism V from B0 to B1 in B equipped with a lift of x1 such that has locally P co-Cartesian lift. And the definition is not finished, but I have to go to the next blackboard. We ask that the class of locally P co-Cartesian morphisms is closed under composition. So now, and if you look at ordinary category theory, that is literally the definition of co-Cartesian fibration in SGA1. Yeah? When we don't define topoi yet, but we define descent. Yeah. Okay, and so now that we know what they are, we can introduce a new axiom. It is about universal properties. Also, maybe before I introduce the axiom, maybe I should give you an example, which I think is a very important one. Is that if you take C, any category, and you look at the category of functor from data 1 to C, that is the category of morphisms of C, and then there is a functor which is called the evaluation at 1, and this is a co-Cartesian fibration. As I said, I didn't give you all the axioms, but they are designed so that this is exactly true. Because you really want this, because you see what co-Cartesian fibrations correspond to is that if you think of them as the fact that you have property 1 means you can literally take pullback, whatever you mean by that, and therefore you can take pullbacks over any point. So you have fibers, and you want that the formation of fibers is functorial in the base B, like fully functorial, not only about equivalences and so forth. And at the end of the day, we want that to have a correspondence between co-Cartesian fibrations and functors with value in the category of categories. And so this will correspond to a functor with and that corresponds to the assignments which to each object of C associate the fiber, the slice. Yeah? And knowing that the slice you can define it as a pullback. See, it is defined from this pullback. And the idea that you want this to be a functor, and a way to say it is a functor is this claim. Yeah? Otherwise, it's not really a functor, because the composition is only up to homotopy. So you really need the notion of vibration to make sense of it, and that's what it is all about. Okay. And then now I can state the axiom of universal properties. So what this axiom says is that if you define a family of objects by universal properties, then this definition is fully functorial. Even if your definition is not functorial, you really check that representability object-wise, period. So a way to say it is for any co-Cartesian vibration, say P, such that for each object B of B, the fiber of P at B has a terminal object SB, there is a fully faithful right adjoint S from B to X of P. So here, again, I won't write it in formulas, because the idea is that you can really mimic all definitions you know. So what it means, for instance, that an object is terminal. I will maybe write it here. So you can say that Y is terminal. That means that for any X, this is equivalent to a point. Yeah? So this is what it means. Okay, why not? Then adjunctions, it will be something similar. That is, you want to say that, or here you could say that you have the delta 1 that you can see as an interval, and you write that it is a kind of strong deformation retract with explicit formulas and stuff like that. Or you can write the formulas using the adjunction formula in terms of ohms, but using this language, for instance. And it can be done in a very naive way. That, of course, you have to check it, but any attempt to provide a definition just works. And if you provide another definition that should be equivalent, it will also work, and everything is fine. So that's why, I mean, I won't spend too much time on that. But it's really, so as I said, everything I said in words always can be interpreted as an actual construction and so forth. Sometimes several of them, and they are equivalent, and everything is absolutely fine. But what it really means, you see, it's really about saying that, another way to say it, maybe, is that, you see, what we are saying is that if you have P, and you have this universal object, so when you pull back, so you can reformulate what I said in words in a way that looks very nice, and in a very global statement, which is that actually, now you see we are in a groupoidal context. So that means that you can interpret this thing as, in fact, a category in groupoidal context. So it's really just plain category. So you can really consider this as a kind of category in a suitable context. And then you are saying that this category, in this context, has a terminal object. This is how you could say it. And what we are saying is that if you have a terminal object in context B twiddle, then in some sense you have a terminal object in context B, also, even if B is not a groupoid now, but in fact you can still formulate the property, and it is true. And that's also another way to state this, right? Fully faithful right adjoints and so forth. So it means you really extend a property of having a terminal object from a groupoidal context to a categorical one. You see, so it means a property for objects only to a fully functorial information. And that is very important because this is how you do in classical mathematics. You see, you provide things, you work object-wise, and because it's defined by universal property, it's a functor. And that's all, any time you want to use this kind of principle, that's this axiom. Okay, then do I have time or not? Or
3 minutes.
3 minutes, that's what I was afraid of. So now that we know all that, so the idea is that we have to, we try to do that in 3 minutes, which is, I think, very challenging. But so we want to define the category of categories. But so we are equipped for that now. So now, so we consider so in some sense, you see, you don't want to define only one category of categories, because if you want to avoid the Russell paradoxes and so forth, so in fact you have to define a hierarchy of category of categories. For each universe, like Grothendieck, in some sense, you should have a category of small categories with respect to this universe, and so you should have many categories of categories. And so in some sense, we want to characterize what is a category of categories. Okay? So you pick a candidate, and so to encourage yourself, you give it the names you want. So it's just a co-Cartesian vibration. And you call the codomain cat because it wants to be the category of categories in some sense. And so you have to say, what does that mean? That it deserves to have this notation. Yeah? And what do you want exactly? So what you want is that first, whenever you define a co-Cartesian vibration, you can say what it means to be small with respect to this vibration. Because you can simply say that whenever you produce a little c like this, you can produce a big C by forming the pullback. And then any C that is obtained up to equivalence by such a procedure will be small with respect to this vibration. Yeah? And more generally, any functor F obtained by a pullback like this will correspond to a co-Cartesian vibration with small fibers in the sense of this one. Okay. So far that you can do that with any co-Cartesian vibration with any name you like. And now you would like to, and what is the principle is that you would like to say that it's like classifying spaces in topology. So you would like to say that the guy here that classifies F, call it like this if you want, should be uniquely determined by F. And that is kind of univalence in some sense. This is what univalence would say, that if you say that this vibration is univalent, it would be exactly this information that the space of such data is the same as the space of such vibrations. But that's not sufficient, because you don't want that only. You want an equivalence of categories. So you want also to say that functors between such things correspond to natural transformations between such functors. Yeah? And so this is exactly what we claim. So this is called directed univalence, because it subsumes ordinary univalence. And it says that if ever you are in this situation, when you have Ci, or maybe since I don't have a lot of time, I think you will forgive me. So you have this for I equals 0 and 1. And then you ask that for any such situation, when you have a pair, then using this universal property, you have to believe me, you can produce a canonical map from. So there is another axiom also I didn't introduce, is that you can define subcategories somehow. Whenever you have a class of morphisms defined in a suitable way in a category, in a synthetic category, you can define the smallest subcategory containing this class of maps. Yeah, you take the closure by composition and so forth. It is what it's supposed to mean. You have to produce a suitable universal property. And then that means that you can look at all co-Cartesian functors. So co-Cartesian functors between co-Cartesian vibrations are defined in the usual way. There is the same definition with the same language. You just write the sentence right away. And so you can define co-Cartesian functors from C0 to C1. And you have a category of such things, and then you can take the groupoid, you just want the collection, or you can look at this category of functors from B, it's not B, it's D, to cat, and then you have two objects in there that are named Fi in between brackets like this, or whatever name you give them. And then using this universal property, you can see that there is a canonical functor like that. Of course, here it comes out of the blue, but it comes very explicitly from the universal property of lifting co-Cartesian edges and so forth. I mean, it's very canonical. And then we claim that this canonical thing is an equivalence. And then the axioms will say that we ask that we have that any abstractly given co-Cartesian fibration is a pullback of such a directed univalent co-Cartesian fibration. And we ask for properties that it is closed under suitable properties. And from there, you can prove absolutely everything. You can prove that these universes have colimit and so forth. You can prove that there is because you can form subcategories, you can form full subcategories. And so you can form S, the full subcategory of groupoids. In there, you can form the full subcategory of zero truncated groupoids, that are the groupoids X, so that the diagonal is a monomorphism, or another way, so that this is a pullback square. That are sets. And then you can check that this is an elementary topos, in the sense we have studied so far. And in there, you can take the full subcategory of subobjects of the terminal object in there, and so forth. And that would be omega with its structure of lattice that we use in the Lurie theory. So this part will correspond to classical logic, like it's really exactly elementary topoi. And so it just means that this truth values, it belongs to the universe, and so these things could be considered as generalized truth value, whatever that means. And we stop here. Thank you very much.